Somewhere near the edge of the observable universe, James Webb found a population of galaxies that should not exist. Not because they are too far away, but because they seem to have arrived before the universe was ready to make them. If those galaxies are real, then one of our most successful stories about how the universe began may be missing something fundamental. These galaxies are not faint beginnings. They are bright, massive, surprisingly mature. They appear at a time when the cosmos should still have been assembling its very first generations of stars, yet somehow they already resemble systems that ought to have taken billions of years to grow. If something in tonight's journey stays with you, a like or a subscribe would mean something real to me, not for an algorithm, but simply because it tells me someone was out there sharing this quiet exploration of the universe. Tonight, we'll follow the oldest light James Webb has ever collected, travel back more than 13 billion years into cosmic history, and step into a region where observation begins to challenge expectation. Whether these impossible galaxies reveal missing pieces of our theories, hidden biases in our measurements, or something even more profound, they are forcing astronomers to ask questions they never expected to ask. So settle in, and let the universe become older, stranger, and far less certain than it seemed just a few years ago. Let's start with the light itself, the actual thing that traveled all that way and landed in the telescope. When we say a galaxy is far away, we're really saying its light is old. The two are the same statement. And the light that reached Webb from the edge of what we can see left its galaxy as a very particular kind of glow. Young galaxies burn hot and blue. They're full of massive stars, the kind that live fast and pour out most of their energy in ultraviolet, the same band that burns your skin at the beach. So the light that set out toward us was not the soft infrared Webb is tuned to catch. It started as ultraviolet. Somewhere along the way, it changed. The light didn't slow down. It didn't lose speed. It didn't bounce off anything. Nothing got in its way. What changed was the space it was traveling through. Over the billions of years that Photon was in flight, the universe kept expanding, and the space between us and that galaxy stretched out underneath the wave the whole time. A wave of light has a length, crest to crest. Stretch the space the wave lives in, and you stretch the wave with it. The crests spread farther apart. Short ultraviolet waves become longer waves. Longer waves become red. And red, stretched far enough, slides right out of the visible range into the infrared. Think about a sound you already know, played back at the wrong speed. The song is the same song, every note in the same order, but everything drops lower, slower, deeper. The pitch fell not from anything you did to the notes themselves, but from the speed of the thing carrying them. Light works the same way here. The color didn't fall because the galaxy dimmed or cooled. It fell as the space carrying it grew. We even have a name for how much it fell. We call it redshift. And for the most distant galaxy Webb has confirmed, the light arrived stretched more than 15-fold from where it started. The wave you're catching now is over 15 times longer than the wave that left. Now, if you're paying attention, something about that should bother you. A stretched-out wave of light carries less energy than a tight one. Shorter, tighter waves are the energetic ones, ultraviolet, X-rays, the stuff that does damage. Long, loose waves are gentle, low-energy, infrared, and radio. So if that photon left as high-energy ultraviolet and arrived as low-energy infrared, we have to ask the obvious question. Where did the missing energy go? The energy wasn't handed off to something else. It wasn't absorbed. It didn't heat anything up along the way. As far as we can tell, it's simply gone from the photon, and it did not reappear anywhere. The rule we all learn, that energy is never lost, only moved around, holds beautifully in a room, on a planet, across a solar system. Stretch your view across an expanding universe over billions of years, and that rule quietly stops being something you can take for granted. There's no fixed shelf to store the energy on when the shelf itself keeps growing. The photon didn't break any law we know. It followed the space it lived in, and the space took some of its energy nowhere at all. We tend to picture the early universe as a place, somewhere far away we're looking at. What Webb is actually reading is a message that changed in transit, over a journey longer than our sun has existed, and we have to run the whole stretching backward in our heads just to know what the message originally said. Every distant color has to be unstretched before we can trust it. We're not seeing the early universe. We're seeing its light after 13 billion years of alteration, and then carefully undoing the alteration. Which brings us to the machine catching all this and one physical problem it had to beat. If we want to see faint infrared from the edge of time, we cannot have the telescope glowing in the same colors we're trying to detect. Anything warm gives off infrared. You do it right now. Your body, at its ordinary temperature, is quietly pouring out infrared light in every direction, which is exactly what night vision goggles pick up in the dark. A telescope sitting at room temperature would blaze in the infrared like a floodlight, drowning out the ancient galaxies completely. So we made it cold. Not chilly. Cold to around 40 degrees above absolute zero, colder than anywhere natural in the entire solar system. Getting it that cold meant getting it away from us. Webb doesn't circle the Earth the way most telescopes do. It sits about 1 million miles out, 4 times farther than the Moon, at a quiet gravitational parking spot, where the pull of the Earth and the Sun balance in a way that lets it hold station cheaply. Out there, it unfolded a shield the size of a tennis court, 5 paper-thin layers, and tucked itself into the shadow behind it. The Sun, caught in the Moon, all sit on one side of that shield. The telescope stares out the other, into the cold and dark, permanently shaded. And then there's the color of the mirror, which isn't a style choice. The mirror is coated in a whisper-thin layer of real gold, a few hundred atoms thick. Silver and aluminum, the metals we normally reach for in a mirror, are excellent for visible light, but comparatively lazy at reflecting infrared. Gold is the opposite. It's a poor mirror for the blue and violet your eyes love, and a near-perfect one for the long infrared waves Webb was built to gather. The telescope is gold, for the same reason its light is red. Both come down to the length of the wave, and which surfaces and which detectors respond to that length. So the photon that started this, the one that left a galaxy as ultraviolet before our sun existed, ends its journey by striking a cold sheet of gold hung in permanent shadow 1 million miles from where you're lying. We can read its stretched color, and from that stretch, read how far the space it crossed has grown. That gives us a number, 15-fold, for the farthest one. But a number for how much the light stretched is not yet a distance, and it isn't yet an age. To turn a stretched color into a moment in the history of the universe, we need one more thing the light carries, hidden inside that glow, waiting for us to notice it. What is it about that light that lets us pin down not just how far it came, but exactly when it left? The thing hidden inside that glow is a set of sharp lines. Not the smooth spread of color you get from a prism catching sunlight, but specific, narrow bright spots and dark gaps at exact positions in the spectrum. Every element makes its own pattern, and it makes the same pattern everywhere. Hydrogen glowing in a lab bench a few feet from you gives off light at precisely the same set of colors as hydrogen glowing in a galaxy at the edge of time. The pattern is fixed by the atom itself, by the rungs an electron can sit on inside it, and those rungs don't care where the atom is or when. Let's stay on why those rungs exist, since the whole method rests on them. An electron bound to an atom can't hold any energy it likes. It's allowed only a specific ladder of levels, nothing in between. When an electron drops from a higher rung to a lower one, it sheds exactly the energy difference between those two rungs, and it sheds it as a single particle of light at exactly one wavelength. Drop between the same two rungs 1 trillion times, and you get 1 trillion photons all the same color. That's what makes a spectral line so sharp. It isn't a range. It's a fixed step, repeated, glowing at one precise pitch of light. Now we do something clever with that. We know where hydrogen's lines sit when the atom is at rest near us. We've measured them to absurd precision. So we look at a distant galaxy, we find that same recognizable pattern of lines, the same spacing, the same order, and we notice the entire pattern has slid toward the red end of the spectrum. The fingerprint is unmistakable, only shifted, every line moved by the same factor. That uniform slide is how we know we're not being fooled. A galaxy that merely looked red from dust or from cool stars wouldn't move the lines. Stretching space moves all of them together, locked in step. This is what separates a real measurement from a good guess. For a while, we can estimate a galaxy's distance just from its overall color, by how red the whole smudge looks through different filters. That's fast, and it's often roughly right, and it's also been wrong enough times to keep everyone honest. A cool, nearby galaxy full of dust can masquerade as a wildly distant one. The only way to be sure is to spread the light out and find the lines, and read how far they've shifted. When Webb did that for the farthest galaxy on its list, the one from the deepest part of that crowded field, the lines were there, and they'd moved by a factor that put the light's departure astonishingly early. Let's put an actual number on it, and then make it mean something. We give redshift a plain label, the letter Z. And for this galaxy, Z came out to about 14. On its own, that number is inert. Here's the part that isn't. Redshift ties directly to how much smaller the universe was when the light left. Add 1 to that number, and you get how many times the universe has expanded since. 14 plus 1 is 15. So every distance in the cosmos back then was around 15 times shorter than it is tonight. A gap between two galaxies that spans 15 million light-years now spanned a single million then. Everything was packed roughly 15 times closer, in every direction. Follow that back far enough and it lands on a time. The light from this galaxy left when the universe was somewhere near 290 million years old. Set that against the full age we measure today, a little under 14 billion years, and it's a sliver at the very front. If we squeezed all of cosmic history into a single year, this light left in the first few days of January, while almost everything we think of as the universe, every later star, every planet, all of it, was still months away from forming. When we say this galaxy is far away, we can mean two different distances, and they don't match. One is how long the light traveled, and that's around 13.5 billion years of flight time. The other is where that galaxy sits right now, tonight, after all those billions of years of space continuing to expand while the light was still in transit. That second distance is far larger, out past 30 billion light-years, well beyond how far the light itself could ever have flown. The galaxy raced away from its own light the entire time the light was coming toward us. That gap between the two distances isn't a trick of bookkeeping. It's the expansion showing up in the numbers directly. The light left a nearby young galaxy in a small, packed universe and spent 13.5 billion years crossing space that kept opening up in front of it and behind it. By the time it reached the gold, its home had been carried 3 times farther out than the distance the light had covered. We catch an object as it was in deep antiquity, while knowing it has long since moved to a place we will never see, glowing now in ways whose light won't reach us for tens of billions of years, if ever. So we've turned a shifted set of lines into a distance, and a distance into a moment near the very beginning. The method is clean, the lines don't lie, and the arithmetic is solid. And it's precisely that solidity that opens the problem this whole night is circling. The measurement is trustworthy. There's no wiggle room to explain away what it tells us, no dust to blame, no filter error to hide behind. We know how far the light came, and we know how young the universe was when it left. Which means we also know how little time that galaxy had to become whatever it was. And when we finally turn from how old the light is to how much light there is, the number stops being a clean triumph and starts being something nobody ordered. How much galaxy can 290 million years actually build? Start with what brightness actually tells us. When we measure how much light a galaxy sends out, and we already know how far away it is, we can work backward to how much light it truly pours out at the source. Distance dims things in a fixed, known way. Undo the dimming with the distance we measured from the lines, and we're left with the real output, the true luminosity, independent of how faint it looks from here. For this galaxy, that number came out high, much higher than a young, still assembling smudge of gas has any way to reach. Luminosity in a galaxy comes mostly from stars, so a high output means a large number of stars, or a smaller number of extremely bright ones, or some mix. Either way, we can convert light into an estimate of stellar mass, the total amount of material locked up in stars. The conversion isn't a single clean multiplier. Bright massive stars produce enormous light per unit of mass, while faint small stars produce very little, so the same glow can come from different amounts of underlying material depending on the mix of star types. We account for that by looking at the shape of the light across many wavelengths, which shifts depending on whether a population leans toward hot, heavy stars or cool, light ones. Run this galaxy through that, and the mass lands in the range of several 100 million times the mass of our Sun, possibly more. Hold on to that figure and set it against the clock we established. 290 million years. That is the entire window this galaxy had, from the first moment any structure could begin to collapse, to the moment its light set out toward us. In that span, it needed to gather gas, cool it, form stars, and build up hundreds of millions of solar masses of them. The problem isn't that this is impossible in principle. The problem is the rate it demands. To reach that mass in that time, this galaxy had to turn gas into stars nearly as fast as the raw physics of gas collapse allows, and hold that pace for essentially its whole existence. We should be precise about what sets that speed limit. Gas doesn't become stars the instant you pile it up. It has to lose its heat first. Hot gas has pressure, and pressure pushes outward against the gravity trying to pull the cloud inward. Until the gas radiates that heat away and the pressure drops, the cloud resists, collapses, and simply sits there, supported by its own warmth. The cooling itself takes time, and it takes something to carry the heat off. In the universe today, that job is done partly by heavier elements, carbon, oxygen, and the rest, which are efficient at absorbing energy and radiating it back out, letting a cloud shed warmth quickly and fall together. Here is where the early timing bites. Those heavier elements didn't exist at the beginning. They're forged inside stars and scattered when stars die. So the very first clouds had almost nothing but hydrogen and helium to work with, and hydrogen and helium are clumsy at cooling. A cloud made of them sheds heat slowly, resists collapse longer, and forms stars less readily than a cloud enriched with the leftovers of earlier generations. Which means the earliest galaxies should have been slow starters, not fast ones. The conditions that make star formation efficient are the ones that take generations of stars to create in the first place. And yet the light says this galaxy was already enriched. Webb didn't only measure its brightness. It caught a specific signature in the spectrum, a feature produced by oxygen. Oxygen is not a starting ingredient. Every oxygen atom in that galaxy was manufactured inside a star that had already formed, already lived, and already died, seeding the gas around it. So, inside that first sliver of cosmic time, this galaxy didn't just form one wave of stars. It formed an early wave, ran them through their full lives, let them die, absorbed what they scattered, and built more stars from the enriched remains. A whole cycle of stellar birth and death, completed before the universe was 300 million years old. We can try to soften this, and people have tried. One route is to say we overestimated the mass. Maybe the light is dominated by a small number of unusually bright stars, so the true amount of material is lower than it first appears. That helps a little, and it's a real effect we take seriously. But it doesn't rescue the timing, since even a reduced mass still demands a completed cycle of star formation and enrichment in the same narrow window. Another route is to blame a black hole, to say the extra light comes from gas heated as it falls into something massive at the center, not from stars at all. That one runs into a wall of its own. The wall is size. A black hole's glow comes from a compact region, gas swirling and heating in a very small volume near the center, which appears to us as a bright point. Stars spread across a galaxy produce light from a broad, extended area. When we look at this galaxy, the light isn't coming from a pinpoint. It's spread across a region hundreds of light years wide. That extent is far too large for a single central engine to explain, and it points back to what we were trying to avoid, a genuinely large population of stars spread across a real galaxy, built impossibly fast. So every escape route narrows to the same place. Lower the mass, and we still need a full stellar life cycle in under 300 million years. Blame a black hole, and the light is too spread out to allow it. The measurement holds from every direction we push on it. This galaxy was massive. It was already salted with the ash of dead stars, and it did all of it in the first breath of cosmic time. One object doing this could be a fluke, a rare early bloomer we happen to catch. The trouble is that when we widen our view from this single galaxy to a full count across the sky, the early universe keeps handing us more light than it should have been able to make. How many of these fast, bright, impossible galaxies are actually out there? Before a count can shut. How fast can gravity pull matter together, at the very fastest, with nothing standing in the way? That speed isn't a matter of opinion. It falls out of one quantity, the density of the material doing the collapsing. Pack matter more densely, and it pulls itself together faster. Spread it thin, and the same collapse crawls. The time it takes for a cloud to fall in on itself depends on how much mass is packed into each volume, and on nothing else. We already worked out that the early universe was around 15 times more compact in every direction. 15 times closer along 3 directions at once means matter packed several thousand times more densely than it is around us tonight. And denser matter collapses faster. Run the numbers on that, and gravity in the early universe ran its collapse roughly 50 times quicker than it does in the thin, spread-out cosmos we live in now. So the early universe wasn't a place where gravity was sluggish. If anything, gravity had the wind at its back. That seems to make the problem easier, and for a moment it does. But collapse doesn't start from a smooth, even sea of matter. If the early universe had been perfectly uniform, every point pulling equally in all directions, nothing would ever have gathered anywhere. The pulls would cancel and the whole thing would just thin out as it expanded. What actually got structure going was unevenness, faint ripples in the density laid down in the first instance, some regions a hair denser than average, some a hair emptier. Gravity works on those ripples, pulling a little harder wherever there's a little more. Follow one of those slightly denser regions forward. It's expanding, along with everything else at first, carried outward by the general growth of space. But its extra density means its own gravity is pulling back a touch harder than its surroundings. Over time, that region expands more slowly than the space around it, falls behind the general expansion, stops growing, and finally reverses and begins to collapse on itself. How long that whole sequence takes depends on how far above average the region started. A region only slightly denser than its surroundings takes a very long time to turn around. A region far denser than average turns around and collapses early. This is where the timing of the first galaxies really lives. The earliest structures could only form in the rarest spots, the extreme peaks, the handful of regions that started far denser than anything typical. Those rare peaks collapse first, and collapse fast, and everywhere else lags behind by hundreds of millions of years. So the model does allow early collapse. It just insists that early collapse is rare, confined to the most extreme fluctuations in the entire density field. A few massive things at the dawn of time sit comfortably inside that. They're the rare peaks doing what rare peaks do. And even after a region collapses, we're not done, since what collapses first isn't the part that shines. Most of the matter pulling everything together is dark matter, which doesn't emit light and doesn't form stars. It gathers into a dense knot first, a halo, held together purely by gravity. Only then does ordinary gas, the hydrogen and helium, fall into that halo, pile up at the center, and begin the separate, slower work of cooling and fragmenting into stars. 2 stages, one after the other. The dark scaffolding assembles, and then the visible part forms inside it. Each stage costs time we don't have much of. Dark matter halos don't appear at full size. They grow from the bottom up, small knots forming first and merging into larger ones, those merging again into larger ones still. A halo massive enough to host a big galaxy is the end product of a long chain of mergers, each of which takes time to play out. You can't skip to a large halo. You have to build it out of smaller ones, step by step, and the steps don't compress. So the full timetable stacks up. A rare, dense region has to turn around and collapse. Its dark matter has to merge upward through a chain of smaller halos into a large one. Gas has to fall in, shed its heat, and only then form stars, which then have to live and die to salt the next round with the elements that let cooling run faster. Every one of those steps is set by physics we can write down, and every one of them eats into the same narrow window of 290 million years. The model doesn't forbid a fast, massive early galaxy outright. It rations them. It says such things exist, and that they're rare, and that we should find only a scattered few of them in the deepest, earliest sky. Which turns the whole question into one of numbers. A single massive galaxy at redshift 14 is a rare peak, and rare peaks are allowed. 2 or 3 more, still fine, still inside the budget of extreme fluctuations the model hands out. The test isn't whether early massive galaxies can exist at all. We've just seen that they can, at the ragged edge of what the timetable permits. The test is how many. Count too many bright galaxies too early, and we're no longer looking at a few rare peaks. We're looking at something the density field was never supposed to produce in that quantity. So when Webb stopped looking at one galaxy and started counting all of them across the early sky, what did the number actually come back as? We don't just tally how many galaxies sit in the early sky. We sort them by brightness, and we ask how many there are at each level of output. How many faint ones? How many middling ones? How many rare bright ones? That distribution, the number of galaxies at each brightness, is the real quantity we compare against the models. It has a shape, and the shape is what carries the information. Faint galaxies are common, and as we move toward brighter and brighter ones, they get rarer fast. Not gently rarer. The count falls off steeply, dropping by large factors for each step up in brightness, so the brightest galaxies should be extraordinarily scarce. This steep drop isn't arbitrary. It traces straight back to what we established about rare peaks. Bright galaxies need massive halos. Massive halos come from the most extreme density fluctuations, and extreme fluctuations are rare in a way that gets more severe the further out you go. So the bright end of the count should thin out sharply, and the earlier we look, the sharper that thinning should become. That's the prediction Webb was measuring against. At redshift 14, in the first few 100 million years, the bright end should be nearly empty, a scattering of rare peaks and little else. What Webb found was a bright end that refused to thin out on schedule. There were far more bright galaxies in the early sky than the steep fall-off allowed, in some counts by factors of 10 or more above the prediction. The faint galaxies behaved. The bright ones didn't. Now we have to be honest about what a surplus of light does and doesn't tell us. Brightness is not the same as mass. An excess of light at the bright end can mean one of two very different things, and separating them is the whole game. Either there genuinely are more massive galaxies than there should be, actual extra material built too fast, or there's a normal amount of material producing an abnormal amount of light per unit of mass. Those two possibilities demand completely different fixes, and for a while the data alone couldn't tell us which one we were seeing. Take the second possibility first, since it's the gentler one. Light per unit of mass isn't fixed. It depends heavily on what kind of stars a galaxy makes. Massive stars are staggeringly more luminous than small ones, out of all proportion to their mass. A star 10 times the sun's mass puts out thousands of times the sun's light, not 10 times. So a galaxy that happens to form an unusually large share of massive stars would blaze far brighter than its total mass suggests, and it would fade quickly too, since massive stars die young. If the early universe favored heavy stars, we'd see exactly this: too much light from not enough mass. There's a real physical reason to think it might have. We already saw that the first gas had almost no heavy elements, and that this made cooling slow. Slow cooling doesn't only delay star formation, it also changes what sizes of stars come out. Gas that can't cool efficiently tends to hold together in larger lumps before collapsing, and larger lumps make heavier stars. So the same lack of heavy elements that should have slowed these galaxies down might also have tilted them toward producing brighter, more massive stars, pumping out extra light without extra total mass. The two effects pull in opposite directions on how bright the galaxy looks. Then there's a third possibility, separate from how many stars there are or how heavy they run. It's about when they form. Star formation doesn't have to proceed at a steady pace. A galaxy can form stars in sudden, intense episodes, brief bursts where it lights up brilliantly, followed by quiet stretches where the bright young stars have died and the galaxy dims. Catch a galaxy mid-burst, and it looks far more luminous than its long-term average. If the early universe ran on these bursts, then at any given moment, a handful of galaxies would be flaring brightly, inflating the bright end of the count, even if their steady-state masses were perfectly ordinary. We'd be counting flashes, not steady lamps. Each of these routes rescues the model a different amount, and each one costs something. Heavy star populations and burst-driven flaring can inflate the light without breaking the timetable, and those are the comfortable answers, the ones that leave the standard picture standing. But they can't be stretched infinitely. Push the brightness excess high enough, or find it consistently rather than in scattered flashes, and eventually you exhaust what tricks of light can explain, and you're forced back to the harder option that there really is too much mass, built too fast, and no amount of clever lighting accounts for it. Which is the real reason this count matters more than any single galaxy did. One impossibly early galaxy could be a rare peak, or a burst caught at the right moment, or a mass we overestimated. A whole population of them, holding steady across the sky, drains those excuses one by one. The more of them we find, and the more consistently bright they stay under closer study, the less room there is to explain the light away, and the more we're left explaining the mass. The count doesn't prove the model is broken. It narrows the space where the model can still be right. And there's a feature of these early galaxies we haven't touched yet, one that has nothing to do with how much light they make or how fast they built their mass. It's about their shape. When we finally looked closely at what these early galaxies actually look like, not how bright they are but how they're arranged, the forms coming back were not the ones the standard picture predicts either. What shape does a galaxy take when it's only just been born? We should be careful about what we even mean by the shape of a galaxy. A galaxy isn't a solid object with an outline. It's a swarm of stars and gas, and its shape is really a description of how all that material is moving. A galaxy like our own is a disk, which is a specific dynamical state, not just a visual one. Nearly everything in it travels the same way, in roughly circular orbits, all in one plane, all going around the same direction. That kind of organized motion is what a disk actually is. The opposite of a disk isn't a different picture. It's disorder. Material moving every which way, orbits tilted at all angles, stars plunging in and out on random paths with no shared plane and no shared direction. A system like that looks puffy and round, and we call it that loosely, but the real distinction is in the motion. A disk is coordinated. A round system is chaotic. And coordination, in physics, is the thing that's hard to arrange and easy to destroy. To see why a disk is hard, we have to talk about spin. Every galaxy has some overall rotation, some net turning, and that turning is a conserved quantity. Angular momentum, the amount of spin a system carries, can't just be created or erased. It gets handed to a galaxy early, before it collapses, by the gravity of its neighbors tugging on it unevenly while it's still spread out. Those off-center tugs give the whole cloud a slow initial turn. Then, as the cloud collapses inward, that turn has to speed up, since the same spin packed into a smaller radius means faster rotation. The galaxy spins up as it shrinks, and that growing rotation is what can eventually support a disk. But rotation alone doesn't make an orderly disk. A cloud can be spinning and still be a mess, with gas moving turbulently on top of the overall rotation. To settle into a thin, flat, organized disk, the material has to shed its disordered motion while keeping its shared rotation. Gas can do this. Gas is collisional, meaning streams of it running into each other collide, heat up, radiate the heat away, and gradually cancel out their random motions, leaving behind only the common circular flow. That settling process is how a chaotic spinning cloud flattens into a clean, rotating disk. And that settling takes time and takes quiet. Quiet is exactly what the early universe didn't offer. We established that galaxies grow from the bottom up, small halos merging into larger ones in a long chain. Every one of those mergers is violent. Two systems fall together. Their stars and gas scramble. Whatever orderly motion either one had gets stirred back into chaos. A galaxy being built by frequent mergers is a galaxy being constantly disordered, its settling interrupted before it can finish. So the standard expectation for the earliest galaxies is disorder, puffy, chaotic systems, still being battered by the mergers that assemble them, with no stretch of calm long enough to settle into a thin disk. That's the prediction Webb was looking at when it examined the actual motions of early galaxies. We can measure those motions directly. The same spectral lines that tell us distance also tell us velocity. Since one side of a rotating galaxy moves toward us and the other moves away, shifting the lines by slightly different amounts across the galaxy's face. Read that shift point by point, and we get a map of how the galaxy is rotating, whether its motion is coordinated or chaotic. When we did this for galaxies deep in the early universe, a good number of them came back rotating in an organized way, with the clean turning signature of settled disks at ages where they should still have been in disordered chaos. The tension here is specific, so let's name it exactly. It isn't that disks can't form early. It's that forming an orderly disk requires a stretch of undisturbed settling, and the merger-driven assembly of the early universe was supposed to deny galaxies that stretch. A settled disk at an age of a few 100 million years means that galaxy found calm the model didn't allow it to have. Either mergers were less frequent or less disruptive than we thought, or gas settled into order far faster than our timeline for it suggests, or something about how these galaxies acquired and organized their spin doesn't work the way the standard sequence lays out. Orderly rotation is not something a chaotic system stumbles into by accident. Disorder is the natural state, the high entropy state, the one a system falls into when it's disturbed. Order is the exception that has to be actively built and actively maintained. Finding coordinated rotation early doesn't just mean a galaxy happened to look neat. It means the specific, time-consuming physics that cancels disordered motion had already run to completion in a setting we thought was too turbulent and too young to let it finish. So we've now got two separate problems stacked on the same early galaxies. They're too bright and too massive for their age, and a good share of them are too organized in their motion for their age. Both point at the same uncomfortable direction. That structure in the early universe came together faster and more completely than the standard assembly sequence permits. And running underneath both of those is a set of objects that doesn't fit cleanly into either problem, because we can't even agree on what they are. Scattered through that same early sky are small, intensely red points of light that have resisted every attempt to classify them. What are we actually looking at when we find one? Let's begin with what actually makes these objects stand out. They're small and they're red, and both of those words carry specific weight. Small means the light comes from a region so compact we can barely resolve it, close to a single point rather than a spread-out galaxy. Red means most of the light arrives at the long wavelength end, with very little at the short end. Put those together and we have an enormous amount of light emerging from a tiny volume weighted heavily toward the red. That combination is what none of our usual categories handle cleanly. The red color alone can happen two completely different ways, and we can't tell them apart from color by itself. One way is age. A population made mostly of old, cool stars genuinely emits more red light than blue, since cooler surfaces radiate at longer wavelengths. The other way is obscuration. A source can be intrinsically blue and blazing, with dust in front of it absorbing the short blue wavelengths and letting the longer red ones through, so it arrives looking red without being red at the source. Same color, two opposite stories, one about what the light is, the other about what sits between us and it. To break that ambiguity, we need more than color, and this is where the spectrum earns its place. Spreading the light out into its full range of wavelengths shows us features color can't. And in many of these red points, the spectrum shows something striking. The emission lines, those sharp, bright features from specific atoms, are broad. Not sharp and narrow the way we described them earlier, but smeared out across a range of wavelengths around their natural position. A line that should sit at one precise pitch instead spans a band. That broadening is a clue, and for a long time it pointed hard in one direction. Here's what broadening usually means. A spectral line spreads out when the gas emitting it is moving at a range of speeds along our line of sight. Some of the gas moves toward us and shifts its light slightly bluer, some moves away and shifts slightly redder, and the line we receive is the sum of all those shifts smeared into a band. The wider the line, the faster the spread of motion. And very broad lines mean very fast motion, gas whipping around at thousands of kilometers per second. The one thing we know that makes gas move that fast in a compact region is the gravity of something extremely massive and extremely concentrated. A black hole. So the natural reading was a black hole feeding at the center. Gas, falling toward a massive black hole, speeds up enormously and heats as it crowds together, glowing brilliantly from a small region, with the broad lines coming from gas orbiting at tremendous speed close in. That would explain the compactness, the brightness, and the broadening all at once. And if we take that reading at face value, we can even weigh the black hole, since the width of the lines tells us the orbital speed, and the orbital speed tells us how much mass sits at the center holding that gas in such fast motion. When people did that arithmetic, the black holes came out enormous. The black hole masses that came out of those broad lines were far too large for the galaxies around them. In the universe nearby, black holes and their host galaxies keep a fairly steady ratio, the black hole a small fraction of the galaxy's mass. These early red points, red as black holes, broke that ratio badly, with black holes far too heavy for the modest amount of starlight around them. And they broke it in the same early window where everything else was already arriving too fast and too heavy. One more thing too massive, too soon. Then a second problem landed on the black hole reading, and this one was harder. Black holes feeding fast are supposed to be loud in X-rays. Gas crushed and heated near a black hole radiates high-energy X-rays as a matter of course, so a population of hungry early black holes should light up when we look in that band. These objects didn't. We looked for the X-rays, and they were strikingly faint, far weaker than actively feeding black holes of that size should produce. The same silence showed up in radio waves. An object bright enough to be a monster black hole, staying quiet in exactly the bands where feeding black holes shout, is a contradiction that sat unresolved. So we were left holding two readings that each failed in a different way. Call them black holes, and we get impossible masses and a missing X-ray glow. Call them dense knots of stars instead, and the compactness and the sheer brightness become very hard to produce without something more than stars. Neither picture closed cleanly. Every attempt to force these objects into a category we already had left some measurement sticking out that the category couldn't absorb. They weren't quite galaxies, weren't quite the black hole systems we knew, weren't quite anything with a name. Every one of these objects is faint in absolute terms, sitting near the edge of the universe. To break the tie between the readings, we need a spectrum deep enough to show not just the bright lines, but the faint details around them, the subtle shape of each line, the weak features hiding beside the strong ones. And on an object this faint, that depth of detail is right at the limit of what even Webb can gather in a reasonable stretch of observing time. We knew the answer was written in the light. We just couldn't collect enough of the light to read it. Which meant the resolution, when it finally came, didn't come from staring harder at a typical one. It came from a rare accident of geometry, one particular red point that nature itself had magnified for us, its faint light bent and amplified by the gravity of something massive sitting directly between it and the telescope. For once, we had enough light. What did the deepest look we've ever taken at one of these objects finally show us? The accident that helped us has a name in physics. A massive object sitting between us and something more distant bends the light passing near it. Mass curves the space around it, and light following that curved space gets deflected, focused, and concentrated, so a faint distant source behind a massive foreground, one arrives brighter and more spread out than it would on its own. A cluster of galaxies happened to sit almost exactly in front of one of these red points, and its gravity magnified that point several times over. The light we couldn't gather enough of, nature gathered for us. With that magnification, we got the deepest spectrum ever taken of one of these objects, and it held far more than the few bright lines we'd managed before. It held dozens of features, faint ones included, the subtle structure around each line that carries the real information. And when we looked closely at how the lines were broadened, the shape told a different story than fast-moving gas. A line broadened by motion has a particular profile, spread evenly to the blue and the red by gas moving toward and away from us. These lines had a sharp, narrow core with broad wings flaring out on either side, and that specific shape doesn't come from bulk motion. It comes from scattering. Light escaping from a source doesn't always travel straight out. If the source is wrapped in a dense enough cloud of free electrons, each photon bounces off electron after electron on its way out, taking a long, randomized path instead of a direct one. Every one of those bounces shifts the photon's wavelength by a tiny amount, since the electron it hits is itself moving. A photon that scatters many times accumulates many tiny shifts, and by the time it emerges, its wavelength has been nudged a little in one direction or another. Collect light from a whole source doing this, and each spectral line gets a narrow, true core, from photons that escaped with few collisions, surrounded by broad wings, from photons that scattered many times before getting out. That distinction changes everything about the mass. The earlier estimates read the entire width of the line as motion, as gas orbiting fast under the pull of a huge central mass. But if most of that width comes from scattering rather than motion, then the gas isn't moving nearly as fast as we thought, and the mass needed to hold it isn't nearly as large. The narrow, true core, the part that does come from motion, points to a far gentler orbital speed. Read correctly. The black hole at the center comes out smaller by a factor of around 100 than the width alone suggested. The monster shrinks. It's still a black hole, still real, but its mass falls into a range that no longer breaks the sky. The same dense cloud of electrons that broadened the lines also answers the other puzzle, the missing X-rays. A black hole feeding at the center does produce X-rays. But if it's wrapped in a thick shroud of gas dense enough to scatter light many times over, those X-rays don't escape freely. They're absorbed and reprocessed by the surrounding material before they can reach us. So from the outside, the object looks X-ray faint, even though a real feeding black hole sits inside. The silence in X-rays and the strange line shapes turn out to be two symptoms of one condition: a black hole buried inside an unusually dense envelope of its own gas. Solve one and you've solved both. A black hole in its rapid early growth, still swaddled in the thick gas it's feeding on, so wrapped in that gas that we see the envelope more than the black hole itself. The compactness, the redness, the brightness, the broad line wings, the quiet X-rays, all of them fall out of that one configuration. The object isn't a contradiction anymore. It's a young black hole caught in the act of feeding, hidden inside the very material that feeds it, at a moment we'd never had a clear enough look to recognize. The alarming version of these objects was the one that read them as impossibly massive black holes, breaking every ratio, demanding new physics. The corrected reading drains most of that alarm. The masses come down, the missing X-rays are explained, and the objects fit into black hole growth we can more or less understand without tearing up the framework. This is what it looks like when a crisis partly resolves, not with a grand new law, but with a careful second look showing we'd misread the light the first time. And I want to sit honestly with the fact that not everything is settled here. This clean reading came from one object, the one nature magnified for us. Hundreds of these red points have been found, and most of them we still can't observe this deeply. Whether every one of them is the same kind of shrouded young black hole, or whether the population is a mix with more than one thing hiding in it, remains open. We solved one case cleanly. We have not yet proven the rest are copies of it. But solving even one case cleanly did something the alarm never let us see. It turned the question from what are these impossible objects into a harder, older question the smaller black hole quietly reopens. Because even a black hole of the reduced mass, sitting there just a few 100 million years after the beginning, still had to come from somewhere. It had to start as something and grow. And when we work out how fast a black hole can actually grow from a small beginning, the early universe runs out of time all over again. Where does a black hole even come from when the universe is barely old enough to have made one? Let's build a black hole the ordinary way first and see where the clock runs out. The straightforward origin is a dying star. A massive star burns through its fuel, loses the outward push that held it up, and its core collapses into a black hole of a few times the sun's mass, maybe a few tens at most. That's a seed. Small, ordinary, the natural end of a heavy star. And from that seed, a black hole grows only one way, by pulling in surrounding matter and adding it to its own mass. The question is how fast that growth can possibly go. There's a hard ceiling on the speed, and it comes from the feeding itself fighting back. Matter falling toward a black hole doesn't drop in silently. It crowds together, heats up, and blazes with radiation on its way in. And that radiation pushes outward on the gas still trying to fall. The very act of feeding produces a glare that shoves away the next meal. So a black hole feeding hard creates its own outward pressure, and that pressure sets a limit on how fast fresh matter can reach it. Feed too hard, and the radiation blows the incoming gas back before it can fall in. That balance point has a definite value, set by a competition between two forces. Gravity pulls the gas in, and radiation pressure pushes it out, and the two scale in a specific way with the black hole's mass. Below a certain feeding rate, gravity wins and matter falls in steadily. Above it, radiation wins and the inflow chokes off. That crossover is the natural speed limit for growth, the fastest a black hole can add mass while still feeding in an orderly way. It doesn't cap the mass a black hole can reach. It caps how quickly the mass can climb. Now let's see what that limit does to the timeline. Growth under this ceiling is not steady addition. A black hole feeding at the limit grows in proportion to its own current mass, which means it grows by multiplying, not by adding fixed amounts. Each doubling takes about the same stretch of time, on the order of a few tens of millions of years. So the mass climbs by repeated doublings, each one taking that same characteristic interval, regardless of how big the black hole already is. To go from a small seed to something enormous, you count how many doublings it takes and multiply by the time per doubling. Run that arithmetic for the early universe, and it strains badly. Start with a seed of a few tens of solar masses, and to reach even the reduced masses we now assign these early black holes, you need many doublings in a row, each eating tens of millions of years, with no interruptions. The universe at that point was only a few 100 million years old. There simply aren't enough doubling intervals available in that window to climb from a stellar seed to the masses we observe, not if the black hole ever paused, ever ran short of gas, ever fed below the ceiling for even a stretch. And real feeding is never perfectly continuous. There's a way to make an ordinary seed work, and it exposes how tight things are. You can let the black hole break the ceiling in short, violent episodes, feeding faster than the orderly limit for brief stretches when gas floods in fast enough to overwhelm the outward push. That's possible, and it may well happen. But leaning on it means admitting the standard limit isn't enough on its own, that early black holes needed bursts of feeding beyond the orderly rate to reach their masses in time. It's a real option, and it's also a confession that the comfortable version doesn't close the gap. The other way out is to start bigger. If the seed itself began not at a few tens of solar masses but at tens of thousands or hundreds of thousands, then the number of doublings needed drops enormously, and the timeline suddenly fits. A heavy seed doesn't have to race. It starts most of the way there. But that just relocates the problem instead of solving it, since now we have to explain how you make a black hole of 100,000 solar masses directly, without waiting for it to grow. A seed that heavy can't be the corpse of a single star. No star that big holds together. And there's a piece of evidence pushing us toward the heavy seed answer, sitting in the very ratios we mentioned earlier. In the nearby universe, a black hole is a small fraction of its host galaxy's mass, the galaxy vastly outweighing the black hole at its center. In the early universe, that relationship looks tilted the other way, with black holes far larger relative to their modest host galaxies than anything we see nearby. The black holes seem to have gotten a head start on their galaxies, arriving heavy while the surrounding starlight was still thin. That's exactly what you'd expect if the black holes didn't grow up slowly from tiny seeds inside their galaxies, but began heavy, ahead of the stars around them. So the seed problem comes down to a fork, and both paths cost us something. Either ordinary stellar seeds grew through repeated episodes of feeding faster than the orderly limit allows, which strains the physics of feeding. Or the seeds were born heavy from the start, which strains our understanding of how you make a massive black hole without a star to make it from. Neither path is comfortable, and the observations lean toward the harder one, the heavy seed, the black hole that was large before it had any right to be. To make a heavy seed directly, we need a large amount of gas to collapse straight into a black hole, all at once, without first breaking apart into stars the way gas normally does. Everywhere else in the universe, a big cloud of gas becomes a cluster of stars, not a single black hole. Something would have to stop that gas from fragmenting into stars and force it to fall together whole. What would it take to make a cloud collapse without ever becoming a star? To understand why gas almost always becomes stars, we have to watch what happens when a big cloud starts to fall together. A cloud collapsing under its own gravity doesn't stay a single smooth object. As it contracts, small, denser patches within it pull inward faster than their surroundings, each becoming its own local center of collapse. The cloud breaks into pieces, and each piece continues collapsing on its own, and those pieces are what become individual stars. This breaking apart is fragmentation, and it's the default fate of nearly every collapsing cloud. A large cloud makes many stars, not one big thing. What controls whether a cloud fragments comes back to something we've already leaned on, the ability of gas to cool? As gas collapses, compressing raises its temperature, and hot gas pushes back with pressure. If the gas can shed that heat quickly, the pressure stays low, and small dense patches can keep collapsing on their own, so the cloud fragments freely into many stars. If the gas can't shed the heat, the temperature climbs, the pressure rises everywhere, and it resists breaking into small pieces. Efficient cooling encourages fragmentation. Poor cooling suppresses it. We saw that primordial gas, almost pure hydrogen and helium, cools poorly. Usually, we treated that as a problem, a reason star formation should have been slow. Here, the same poor cooling becomes the thing that might let a heavy seed form. A cloud of primordial gas that can't cool efficiently resists fragmenting into many small stars, and instead tends to stay together as a single collapsing mass. The very inefficiency that slowed star formation elsewhere is what could keep a cloud whole long enough to fall together as one. But hydrogen and helium do have one cooling channel that spoils this, and it has to be shut off. Even without heavier elements, hydrogen can form molecules, two hydrogen atoms bound into a pair, and molecular hydrogen is a modest coolant. It's not efficient, but it's enough to let a primordial cloud cool somewhat, fragment somewhat, and make stars, which is the ordinary path. To force a cloud to collapse whole instead, you have to disable even that weak cooling. You have to destroy the molecular hydrogen faster than it can form, leaving only the atoms, which cool far worse. There's a specific way to do exactly that, and it depends on a nearby source of light. Molecular hydrogen is fragile in a particular band of ultraviolet radiation. Light in that band, sitting at energies just below what it takes to ionize hydrogen outright, breaks the molecules apart, splitting the pairs back into single atoms before they can build up enough to cool the cloud. So a cloud bathed in enough of that ultraviolet keeps getting its molecular hydrogen stripped away as fast as it forms. It's left with only atomic hydrogen, only the poor cooling, and it resists fragmenting. Where that radiation comes from is the neat part of the picture. A cloud sitting next to an already forming galaxy, one that's making hot young stars, gets flooded with exactly this ultraviolet light from its neighbor. So the setup requires a particular arrangement, a pristine cloud of primordial gas sitting close enough to an early star-forming galaxy to be bathed in its ultraviolet, but not so mixed with it that it gets polluted by heavy elements. Under that specific condition, the cloud's molecular hydrogen stays destroyed, its cooling stays poor, and it resists breaking into stars. It stays whole. Now follow that whole cloud as it collapses without fragmenting. Instead of splitting into many stars, it falls together into a single enormous concentration of gas. That object can briefly become a supermassive star, a single star far larger than anything that forms today, hundreds of thousands of times the sun's mass, held up only weakly against its own gravity. A star that large is desperately unstable. It can't sustain itself the way ordinary stars do, and it collapses quickly, its core falling straight into a black hole while much of the gas is still raining in. The result is a black hole born heavy, tens of thousands to hundreds of thousands of solar masses, without ever having lived as a normal star. That's the heavy seed the timeline demanded, and notice how it connects back. A seed born at 100,000 solar masses needs far fewer doublings to reach the masses we observe, and suddenly, the growth fits inside the few 100 million years available. The seed problem and the fragmentation problem solve each other. The same primordial gas that cools poorly, in the specific setting of a nearby ultraviolet source destroying its molecular hydrogen, produces exactly the kind of massive seed that the black hole growth calculation was begging for. The pieces fit, which is part of why this picture is taken seriously. And it links forward, too, to the objects we spent so long trying to name. A heavy black hole seed, freshly formed, still buried in the enormous cloud of gas it collapsed out of, feeding on that gas while wrapped inside it. That description is close to what we finally read off the one red point nature magnified for us, a young black hole shrouded in its own dense gas. The direct collapse seed and the shrouded feeding black hole may be two views of the same phase, the beginning and the early growth of a heavy black hole born without a star. The scenario predicts the object, and the object may be the scenario caught in the act. We haven't watched a cloud collapse directly into a heavy seed. The conditions it needs are specific, and how often the early universe actually arranged them is unknown. What we have is a chain of physics that hangs together, that solves several problems at once, and that points at objects we're now finding. That's strong, and it's not the same as proven. Black holes, though, weren't the only thing arriving too early with no clear way to have formed. The early universe also handed us solid dust, and dust, like heavy seeds, is supposed to take time and dead stars to make. How does a young universe manufacture dust before it has had time to make it? Let's be precise about what a dust grain actually is, since the word sounds too ordinary for what it demands. Cosmic dust isn't dirt. It's solid particles, tiny grains built from heavy elements locked together, carbon bonded into solid form, or silicon and oxygen and metals assembled into mineral grains. And every one of those heavy elements has the same origin we keep running into. Carbon, silicon, oxygen. None of them existed at the beginning. They were all forged inside stars, out of the original hydrogen and helium, and released only when those stars died. A dust grain is a small assembly of stellar ash. So making dust takes two separate things, one after the other. First, the heavy elements themselves have to be manufactured inside stars and scattered into space. Then those scattered atoms have to find each other in the cold and bond into solid grains. Neither step is instant. Stars have to form, live out their lives, and die to produce the raw material, and only then can the grains begin to assemble from what the dead stars left behind. Both steps cost time, and time is the one thing the early universe keeps not having enough of. There are two known places where dust gets made, and we should look at each, since each has a timing problem here. The first is the slow one. Stars near the ends of their lives, but not massive enough to explode, swell into cool, bloated giants and shed their outer layers gently into space. In those cool, dense, outflowing envelopes, atoms of carbon and other elements have the low temperatures and the density they need to bond into grains. This is a genuine dust factory, and a productive one. The trouble is which stars do it. The stars that make dust this way are modest in mass, and modest stars live a long time, hundreds of millions to billions of years, before they reach the dust-making stage. That timing simply doesn't fit the early universe. A galaxy only 200 or 300 million years after the beginning hasn't existed long enough for its modest stars to have aged into that phase. Those stars are still in the prime of their lives, nowhere near the gentle shedding stage that makes dust. So the slow factory, the one responsible for a great deal of the dust around us today, can't have run yet in a galaxy that young. It hasn't had time to switch on. That leaves the fast factory, and it comes with its own contradiction. Massive stars live short lives and die in explosions, and those explosions forge heavy elements and can condense some of them into dust grains as the blast cools and expands. This is fast enough to fit even the early universe, since massive stars live and die in just a few million years. A young galaxy could absolutely have run its massive stars through their short lives and their explosions inside the available window. So far, the timing works. The problem with the fast factory isn't when it runs. It's whether the dust it makes survives. Here's the contradiction inside the explosion. The same blast that forges the dust also sends a shock wave tearing outward through the surrounding gas. And when that shock, or its rebound, passes back through the freshly made grains, it can shatter them and blast them apart, breaking the solid grains back down into individual atoms. So an exploding star is both a maker and a destroyer of dust, building grains in the cooling ejecta and then threatening to demolish them with its own shockwave. How much dust actually survives that self-destruction is genuinely uncertain, and it may be only a small fraction of what was made. So we're caught between two factories that each fail a different way. The slow one, the aging modest stars, makes dust reliably but hasn't had time to start in a galaxy this young. The fast one, the exploding massive stars, runs quickly enough but may destroy much of its own product before it can accumulate. And yet when Webb looked at galaxies in that early window, the signature of dust was there. And in some cases, the specific signature of carbon-rich dust in particular, present in real quantity, far more than the surviving output of a few explosions seems able to supply. Perhaps the explosions don't need to deliver finished, surviving grains. Perhaps they only need to deliver the raw heavy atoms into space, and the grains then grow afterward, out in the cold gas between the stars, where atoms stick onto whatever tiny seed grains survived and build them up over time. In the cold, dense pockets of interstellar gas, grain growth can continue quietly, adding material atom by atom, well away from the shock waves that shattered the originals. That relocates the dust making from the violent explosion to the calm space around it. Grain growth in interstellar gas takes its own time, and whether it can run fast enough to build the observed dust inside a few 100 million years is still being worked out. What we can say is firm. The dust is there, early, in amounts that stretch our accounting, and every route to making it runs into either a timing wall or a survival wall. Solid grains of stellar ash existed when the universe had barely had time to make its first ash at all. And notice what dust quietly proves, no matter which factory made it. Dust is heavy elements, and heavy elements are the leftovers of dead stars. Its mere presence means whole generations of stars had already formed, lived, and died in that early window, seeding the gas with carbon and oxygen and metals before the light we're looking at even left. The first stars did their work and were gone. And those first stars, the ones that made everything else possible, left another mark on the entire universe at once, written not in a single galaxy but across all of space. The gas between the galaxies changed state, and that change carries its own impossible timing. How did the whole universe go from opaque to clear so soon? Let's establish why the early universe was opaque at all, since that's the state everything started from. A few 100,000 years after the beginning, the universe cooled enough for electrons to settle onto protons and form neutral hydrogen atoms, filling all of space with a thin gas of neutral hydrogen. And neutral hydrogen has a specific appetite. It readily absorbs ultraviolet light, swallowing any photon energetic enough to knock its electron loose. So space filled with neutral hydrogen is not transparent to ultraviolet. Light in that band gets absorbed before it travels far, and the universe sits fogged to it, opaque across the very wavelengths young hot stars pour out most. Today, that same intergalactic gas is transparent, and ultraviolet light crosses vast distances freely. The difference is that the hydrogen out there is no longer neutral. It's ionized, its electrons stripped away again, split back into free protons and electrons. And ionized hydrogen doesn't absorb the way neutral hydrogen does, since the electron that did the absorbing has already been torn off. So, at some point, the neutral fog was ionized nearly everywhere, and space cleared. That clearing is what we call reionization. To ionize hydrogen across all of space takes a specific thing, and this is the crux. It takes ultraviolet photons, one for each hydrogen atom torn apart, energetic enough to strip the electron away. And not just once. Out in the thin gas, a freed electron and proton occasionally find each other and recombine back into a neutral atom, which then has to be ionized all over again. So keeping the universe ionized means supplying enough ultraviolet photons to overwhelm every hydrogen atom and to stay ahead of the ones that keep recombining. The whole process is a photon budget, a tally of how many ionizing photons the universe can produce against how many it takes to clear and hold the fog. We can actually measure when the fog cleared, and the tool is elegant. We look at the light from very distant bright sources shining through the intervening gas toward us. Wherever that light passed through neutral hydrogen, the neutral gas absorbed the ultraviolet, cutting a piece out of the spectrum. Wherever the gas was already ionized, the light passed through untouched. So by reading which parts of a distant source's spectrum survived and which were absorbed, we can tell how neutral or ionized the gas was at different distances, which correspond to different times. The spectrum becomes a record of the fog lifting, stage by stage, as we look at sources farther and farther back. What that record shows is that the fog cleared early and fairly sharply. The universe went from mostly neutral to mostly ionized within the first several 100 million years, largely complete by around 1 billion years in. That's a large volume of gas to ionize all of intergalactic space and to keep ionized against recombination in a short stretch of cosmic time. Which sends us straight back to the budget. Where did all those ionizing photons come from, and were there ever enough of them? The obvious source is the galaxies we've been discussing, and here the accounting gets tight. Hot young stars produce ultraviolet photons in abundance, so early star-forming galaxies are the natural candidate. But there's a catch in getting those photons out. A galaxy is full of its own gas, and much of the ultraviolet a star produces gets absorbed by the galaxy's own hydrogen before it ever escapes into intergalactic space. Only a fraction of the ionizing photons a galaxy makes actually leak out to do the work of clearing the fog. That fraction is small, and it's hard to measure, and the whole budget hinges on it. So the question becomes whether the early galaxies could really supply enough. If only a small fraction of their ultraviolet escapes, you need a great many galaxies, producing a great deal of ultraviolet to clear all of space on the schedule we measure. And this is where reionization stops being a separate puzzle and starts rhyming with everything else. The early universe cleared its fog faster than an easy accounting of known sources seems to allow, just as it built mass faster, organized faster, and made dust faster than expected. The timing runs ahead of the supply, again. Perhaps the early galaxies leaked ultraviolet far more efficiently than galaxies do now, letting a larger fraction escape. Perhaps there were many more faint small galaxies than we've counted, each contributing a little, adding up to enough. Or perhaps galaxies aren't the whole story, and another kind of source was pumping out ionizing radiation alongside them. Each of those shifts the accounting a different way, and each points at a different picture of what the early universe was actually full of. The black holes we spent so long on, feeding and blazing in the early universe, are themselves powerful sources of ionizing radiation. If there were more of them, or if they were more active than we assumed, they could have contributed to clearing the fog alongside the stars. The same objects straining one part of the accounting might help balance another, which means the reionization budget and the black hole count are not separate books. They're entries in the same ledger, and how we settle one changes the other. So we're left with a clearing that happened too soon for the sources we can easily count, and a set of possible fixes that each rearrange what the early universe contained. Too many faint galaxies, or too much leakage, or too many active black holes, or some blend of all three. Every fix costs something, and none is yet decisive. But push on any of them hard enough, and they all lead to the same deeper place, past the light, past the gas, to the thing that shaped where all these galaxies and black holes could form in the first place. What was actually holding the early structure together, and why do its own footprints refuse to line up? There's a second record of reionization we haven't used yet, and it comes from an unexpected direction. The oldest light in the universe is the glow released when the first neutral atoms formed, the radiation that has been traveling ever since from every part of the sky. That light was set free before reionization, and it has crossed the entire universe to reach us, which means it passed through all the gas that later got ionized. And ionized gas does something to light passing through it. The free electrons scatter it, nudging the photons off their paths, slightly blurring and dimming that ancient glow by an amount that depends on how many free electrons it crossed. That gives us a completely separate handle on the total amount of ionization. The more the universe was ionized, and the earlier it happened, the more free electrons that old light had to cross, and the more it got scattered along the way. We can measure that scattering as a single number, a total accumulated dimming imprinted on the ancient glow. And that number sets a ceiling. It tells us the total quantity of ionization the universe underwent, integrated across all of time, independent of any galaxy count. Whatever sources cleared the fog, their combined work has to add up to that measured amount, no more and no less. This is where a surplus of early photons becomes its own kind of trouble. We've been treating the problem as a shortage, not enough photons to clear the fog on schedule. But push the fix too far in the other direction, pile in too many early sources leaking too freely, and you ionize the universe too early and too completely. That would pile up more free electrons, earlier, for the ancient light to cross, and it would scatter that light more than we measure. The measured dimming is modest. It rules out a universe that ionized itself in a sudden early flood. Too many photons too soon contradicts the oldest light we have. So the budget is squeezed from both sides at once, and this is the real bind. The pace at which the fog cleared demands a healthy supply of ionizing photons, enough to overcome the shortage. The scattering imprinted on the ancient glow forbids too large a supply too early, capping the surplus. The solution has to thread between them, producing enough photons to clear the fog on time, but not so many, so soon, that the ancient light would carry a heavier mark than it does. It's a narrow corridor, and every proposed source has to fit inside it. Now we can see why counting faint galaxies and active black holes matters so precisely. Each candidate source has to be added to the ledger in a way that lands inside that corridor. Add too few and the fog clears too slowly. Add too many, or turn them on too early, and the ancient light scatters too much. The abundance of early galaxies Webb keeps finding pushes the count up, which helps the shortage but risks the ceiling. The active black holes push it up further still. Reconciling the whole picture means finding a combination of sources, escape fractions, and timing that satisfies the pace, the ceiling, and the raw galaxy counts all together, and that combination is not yet nailed down. This is not a contradiction that breaks physics. It's an accounting that hasn't closed, with real uncertainty in nearly every term. We don't firmly know the escape fraction. We don't have a complete count of the faintest galaxies, and we don't know how much the black holes contributed. Each of those could shift and bring the books into balance without anything exotic. What makes it more than bookkeeping is the pattern, that the same early epoch keeps demanding more activity, sooner, than the straightforward accounting supplies, across mass, structure, dust, and now ionization. And the ancient glow that capped the photon budget carries more than one message, which is what pulls us deeper. That same light is not perfectly smooth. It's very slightly brighter in some directions and fainter in others, in a faint pattern spread across the whole sky. Those tiny variations are a direct picture of how matter was distributed at that early moment, the faint, denser, and emptier regions we said gravity would later work on. The scattering told us how much the universe ionized. The pattern tells us how lumpy it was to begin with, the seed map from which every galaxy and black hole eventually grew. That seed pattern is where the real foundation of this whole story sits. Everything we've followed, the fast galaxies, the heavy seeds, the early dust, the quick clearing, all of it grew out of those initial variations under the pull of gravity. And most of the matter doing that pulling was never any of the gas or stars we've been discussing. It was the unseen matter, the dark component that outweighs everything visible several times over and provided the gravity that gathered the ordinary gas in the first place. The seed pattern in the ancient light is largely a map of where that dark matter was, denser here, thinner there. So the early universe kept running ahead of schedule, and underneath every one of those schedules was the same invisible framework setting the pace. The dark matter gathered first, and everything visible formed inside the wells it made. If structure came together too fast, the framework that drove it is the first place to look. And that framework is the one part of this entire story we have never touched directly, never seen, never caught in any instrument, known only by the gravity it exerts. What is the thing that built the scaffolding, and why has it stayed completely invisible while shaping everything we can see? Let's start with why we think there's anything invisible there at all. We don't infer dark matter from one measurement. We infer it from the same discrepancy showing up in unrelated places. Galaxies rotate too fast at their edges to be held together by the gravity of their visible matter alone, and they'd fly apart without extra unseen mass. Clusters of galaxies move too quickly to stay bound by their visible mass either. The way light bends around massive structures reveals more gravity than the glowing matter can account for. Different measurements, different scales, all pointing at the same missing mass. And there's a lot of it, several times more than everything visible combined. For every unit of ordinary matter, the stars and gas and dust and planets, there's roughly 5 times as much of this unseen material. It doesn't emit light, doesn't absorb it, doesn't interact with radiation in any way we've detected. It makes itself known only through gravity, which means the universe we can see, all of it, is the minority component formed inside the gravity of a majority we cannot see at all. That invisible majority is what built the structure, and the sequence matters. After the beginning, the ordinary gas was still too hot and too pressurized to gather on its own, pushing back against collapse with its own heat. The dark matter had no such problem. It doesn't feel radiation pressure, doesn't heat up the way gas does, so it could begin gathering under gravity earlier, sinking into the denser regions of that seed pattern while the ordinary gas was still resisting. The dark matter gathered first and made the wells. Only later did the gas cool enough to fall into those already formed wells and start making stars. So the shape and timing of everything visible was set by how the dark matter gathered. Where it pooled deeply, gas followed and galaxies formed. Where it stayed thin, little formed at all. The whole architecture of the cosmos, where galaxies sit, how they cluster, when they could begin, traces the distribution of a substance we've never directly detected. And that means the details of how structure formed early, the very timing we keep finding too fast, depend on the exact properties of this unseen material. Here's where different kinds of dark matter start to matter, and they differ in one main property: speed. The particles that make up dark matter are moving, and how fast they move early on shapes what they can build. Fast-moving particles resist being gathered into small clumps, since their speed carries them out of any small region before gravity can hold them, smearing out fine structure. Slow-moving particles gather into clumps of any size, right down to small ones, since they don't have the speed to escape even a modest gravitational pull. The typical speed of the particle sets the smallest structure it can form. The standard picture uses slow, heavy particles, and this is the version everything so far has assumed. We call it cold dark matter, cold meaning slow-moving, and it has a clear consequence. Slow particles clump on every scale, including the smallest, so structure builds from the bottom up, tiny clumps forming first and merging into larger ones over time. This is the merger-driven, bottom-up assembly we leaned on when we said early galaxies should be disordered and slow to build. Cold dark matter predicts a universe assembled gradually, small pieces first, through a long chain of mergers. And it's precisely that gradual, merger-heavy timeline that Webb keeps finding violated. So people have looked again at the alternatives, which change that one property. One is warm dark matter, made of lighter, faster-moving particles. Faster particles wash out the smallest clumps, so structure can't build from the very bottom. Instead, the first structures form along larger, smoother patterns, and small clumps are suppressed. That shifts how and when the earliest galaxies come together, and it changes the shapes they start with. A universe with warm, dark matter forms its first structures along smooth, extended features rather than through a swarm of tiny, merging clumps. The other alternative is stranger, and it treats dark matter not as ordinary particles at all. In this picture, the dark matter is made of particles so extraordinarily light that their quantum nature spreads them out over enormous distances so that each one behaves less like a point and more like a wave, with a wavelength spanning the size of a galaxy. On large scales, it still gathers under gravity and mimics the standard behavior. But on small scales, the wave nature resists compression, smoothing out fine structure and setting a minimum size below which clumps simply can't form. This wave-like dark matter also suppresses the smallest structures by a completely different mechanism than speed. Notice that both alternatives do something the standard cold version doesn't. They suppress the smallest clumps and favor structure forming along smooth, extended features rather than through endless mergers of tiny pieces. And structure that forms along smooth features rather than by chaotic merging would come together differently, possibly faster in some respects, and with different initial shapes, which connects directly to the two things Webb found and we set aside. The early galaxies were too organized in their motion and, as we're about to see, oddly elongated in their forms. Both of those are exactly the kind of clue that could tell us which version of dark matter we actually live in. So the invisible framework isn't just a backdrop to the crisis. It might be the source of it. If the early universe assembled faster and more smoothly than expected, the properties of the dark matter that drove that assembly are the natural suspect, and the shapes of the first galaxies become a way to read those properties off the sky. We have three candidates, differing in how fast their particles move, or whether they behave as particles at all, each predicting a different early universe. And for the first time, we have images of galaxies young enough to tell them apart. What shape did the very first galaxies actually take? Let's be careful about what we mean by an elongated galaxy, since shape can fool us. A galaxy that looks stretched out in an image could be genuinely elongated, or it could be a flat round disk that we happen to be viewing edge-on, so it only appears as a thin streak from our angle. Those are completely different three-dimensional shapes that can produce the same flat image. So before reading anything into elongation, we have to rule out that we're just catching disks from the side. That distinction is the whole battle in this measurement, and it's why a single stretched galaxy proves nothing on its own. The way past that is to look at many galaxies at once and let the statistics decide. If the early galaxies were flat disks seen from random angles, we'd catch them at every orientation, some face-on and round, some edge-on and thin, and every tilt in between. That mix produces a particular spread of apparent shapes, and we know what that spread should look like. When we instead measure the actual distribution of shapes across a large sample of early galaxies, and it doesn't match the pattern that random disks would give, we can rule out the edge-on explanation. The shapes come out genuinely elongated, stretched in 3 dimensions, not flat disks caught from the side. That 3-dimensional shape has a name, and it's a specific geometry. A prolate shape, stretched along one axis and narrower in the other two, longer than it is wide in a real physical sense. And when the counts came in, a striking share of the earliest galaxies came out prolate, elongated along one direction, at a stage when the standard picture predicts something else entirely. The cold, merger-driven assembly we described tends to produce roundish shapes, since a galaxy built by mergers coming from all directions gets stirred into a rough spheroid. Elongation along a single axis is not what chaotic merging from all sides naturally makes. So the shape itself is a clue about how these galaxies were assembled. A galaxy stretched along one axis suggests it was built by matter flowing in along one direction, fed from a preferred line rather than gathered from all sides at once. Material streaming in along a single smooth channel would pile up into an elongated form, drawn out along the direction of the flow. That kind of directional feeding is exactly what the alternative dark matter models produce, where structure forms along smooth, extended features rather than through mergers from every direction. The shape points away from chaotic merging and towards smooth, directed inflow. You can't run the real universe twice with different dark matter. What you can do is simulate a patch of universe under each candidate, cold, warm, and wave-like, letting each build galaxies according to its own rules, and then look at the shapes each one produces in that first stretch of cosmic time. Feed each model the same starting conditions, run them forward, and read off the distribution of galaxy shapes each predicts. Then set those predicted distributions against the shapes Webb actually measured. The warm and wave-like dark matter simulations, which build structure along smooth filaments during the first several 100 million years, produce the kind of prolate, stretched galaxies that were showing up in the data. The cold model, building through mergers, leaned more toward rounder shapes and matched less well. The shapes of the youngest galaxies, in other words, looked more like the universe the alternatives predict than the one the standard model does. The forms lined up with directed, filament-fed growth. And the remarkable part is that this comparison can point at an actual number. The speed of the dark matter particle, the property that separates the models, controls how thoroughly small structure gets smeared out, which in turn shapes how elongated the early galaxies come out. So the degree of elongation is tied, through the simulations, to the mass and speed of the particle. Read the shapes carefully enough, and you can start to estimate what kind of particle produces them, whether a warm particle of a certain mass or a wave-like one of a certain extraordinarily tiny mass. The geometry of galaxies becomes a way to weigh a particle nobody has ever caught. This is a genuinely exciting line of evidence, and it is not a settled result. The samples are still modest. The shape measurements are hard at these distances, and separating true elongation from every observational effect takes great care and remains contested. There are researchers who read the same shapes as still consistent with the standard model once all the complications are folded in. What we have is a real and repeatable tendency toward elongated early galaxies, and a serious argument that it favors the alternatives, not a proof that cold dark matter is wrong. But even held carefully, notice what has happened here. A property of a particle we've never detected, a substance known only through gravity, might be readable in the shapes of galaxies at the edge of time. The same early universe that keeps assembling too fast is showing us forms that could point to what the assembly was made of. The excess brightness, the early order, the fast-built mass, and now the stretched shapes, all of them lean the same way toward an early universe that came together more smoothly and more quickly than the standard framework expects. Every separate thread is pulling in one direction. We have a framework that succeeds almost everywhere, and a specific early epoch where crack after crack keeps appearing, each one small, each one contested, all of them landing in the same era and leaning the same way. That's a peculiar situation, and it demands a clear-eyed reckoning rather than either panic or dismissal. What does it really mean when a theory that works is failing in exactly one place, over and over? The standard framework of cosmology works. It predicts the pattern in the ancient light with extraordinary precision. It predicts how much hydrogen and helium the early universe made, and the measured amounts match. It predicts how galaxies cluster across enormous stretches of the sky, and the clustering matches. This is not a broken theory. It's one of the most successful descriptions of nature we have ever built, correct across 1,000 independent tests. And it keeps cracking in exactly one place, not scattered randomly across its domain, which is what genuine failure usually looks like. Every crack we've followed tonight lands in the same narrow window. The first few 100 million years, the earliest structures, the deepest reach of what we can see. Too much light there. Too much order there. Mass built too fast there. Black holes too heavy there. Dust too soon there. Shapes too stretched there. One epoch, failing repeatedly, while everything after it holds. A theory that failed everywhere would be simply wrong. A theory that fails in one bounded region, while succeeding on either side of it, is usually telling us something narrower. Either we're measuring that region wrong, or we're missing some piece of physics that only matters there, or the foundation itself has a flaw that only shows under the extreme conditions of that region. Those three are very different diagnoses, and the honest position is that we don't yet know which one we're facing. Take the first, that we're measuring it wrong. The early universe is the hardest place to measure anything. The galaxies are faintest, the light most stretched, the corrections largest, the room for systematic error widest. Some of what looked impossible has already dissolved under better measurement, as we saw with the red points, where a careful second look cut the black hole masses by a factor of 100 and drained most of the alarm. It's entirely possible that more of these cracks are measurement artifacts that will close the same way, one careful correction at a time. Take the second, that we're missing physics that only matters early. Not a flaw in the foundation, but an incomplete accounting of how gas and stars behave under early conditions. The rate stars form, the sizes they come in, how radiation escapes a young galaxy, how black hole seeds are made. All of these are messy details layered on top of the framework, not the framework itself. Getting those details wrong could produce every early anomaly without the underlying model being wrong at all. Much of the current work is exactly this, adjusting the astrophysics of early stars and gas to see how much of the strangeness it absorbs. And take the third, that the foundation itself is incomplete. This is the possibility that the nature of dark matter, or something equally deep, is not quite what the standard model assumes, and that the early universe is simply the one place extreme enough to expose it. The elongated shapes hint in this direction, and if they hold, they wouldn't be a measurement error or a detail of star formation, but a clue about the fundamental substance itself. This is the most consequential reading, and the one that needs the highest bar of proof, since replacing part of the foundation is not something the evidence yet forces on us. History gives us both outcomes, and it's honest to hold both in view. There was a time when the orbit of a planet refused to match the prevailing theory of gravity, a small, persistent anomaly that wouldn't go away. One such anomaly, in the orbit of Mercury, turned out to be real, and resolving it required a deeper theory of gravity that replaced the old foundation. Another anomaly, in the orbit of Uranus, was resolved not by new physics at all, but by an unseen planet nobody had yet found, sitting comfortably inside the existing theory. The same kind of stubborn discrepancy led, in one case, to a revolution, and in the other, to a discovery that confirmed the old rules. So a persistent crack is not, by itself, a verdict. It's a question that stays open until the measurements get good enough to answer it, and the discipline of the field is to resist answering it early in either direction. The standard is deliberately severe, demanding a level of certainty that treats a 1 in a million fluke as still too likely to trust, precisely so that neither excitement nor stubbornness settles the matter before the data does. That severity is why cosmologists have not thrown out the standard model over these cracks, and also why they cannot ignore them. Both responses would be a failure of the same discipline. But here is the thing the pattern leaves us holding, quietly, underneath all the caution. Every one of these cracks sits in the chapter of cosmic history we understood the least until a few years ago, the chapter we had almost no direct light from until this telescope existed. We built the standard model largely from the universe we could already see, the later universe, the nearer one. The earliest stretch was filled in by extrapolation, by running the successful later physics backward into a time we couldn't yet observe. And the moment we finally got real light from that stretch, it started disagreeing. The cracks are concentrated in precisely the era we had never actually checked. We're not watching a solid theory break. We're watching the first real test of a region we'd only ever assumed, and finding that our assumptions about the beginning don't quite match what the beginning actually did. Whether that resolves into better measurements, or missing astrophysics, or a genuinely new foundation, the beginning is turning out to be less settled than the confident timeline suggested. And there's one part of that beginning we still haven't seen at all, a generation of objects that had to exist for any of this to follow, and that no telescope has yet confirmed. What did the very first stars actually look like, the ones that started all of it? Let's reason out what the first stars had to be like, since we've never seen one and have to build them from physics alone. They formed from the only material that existed then, hydrogen and helium, with none of the heavier elements that came later. And we already know what that composition does to gas. It cools poorly. We used that fact twice already, once to explain why early star formation should have been slow, and once to explain how a cloud might collapse whole into a heavy black hole seed. Here it shapes the ordinary stars themselves, and it drives them toward one extreme. Follow a cloud of pure hydrogen and helium as it collapses. To form a star, a piece of that cloud has to cool and shed its heat so it can keep contracting. With no heavy elements to carry heat away efficiently, the gas stays warmer than a modern cloud would, and warmer gas resists collapsing into small pieces. So a primordial cloud tends not to fragment into many small stars. It holds together in large lumps, and each large lump becomes a single, very massive star. The same poor cooling that slows everything down also forces the first stars to be enormous, far heavier than typical stars forming today. That mass sets everything else about them. A very massive star burns its fuel furiously, blazing far hotter and brighter than the sun, pouring out most of its light in the ultraviolet. And it burns through its fuel fast. A star tens or hundreds of times the sun's mass lives only a few million years, a flicker against cosmic time, before exhausting itself and dying. So the first stars were massive, blindingly hot, ultraviolet heavy, and short-lived, gone almost as soon as they appeared. Which is a large part of why we've never caught one. Their brevity is the first obstacle to finding them. They existed only in the earliest moments, and each one lasted only a few million years. By the time light from that era reaches us, stretched and faint, the window in which these stars shone is vanishingly thin. And once the first generation died, they salted their surroundings with the heavy elements they'd forged, so every later star formed from gas that was already polluted. The pure, heavy element-free stars could only exist before that pollution spread, in a brief opening at the very start, and possibly in isolated pockets that stayed pristine a little longer. So we don't look for them by their light directly, which is too faint and too brief to catch easily. We look for their fingerprint, a specific combination that only they would produce. A region glowing with the signatures of intense ultraviolet radiation and hot ionized helium, but showing no trace of heavier elements, no carbon, no oxygen, none of the pollution that every later population carries. That combination, fierce radiation with a complete absence of heavy elements, is the signature of stars made purely from primordial gas. Finding radiation that strong with a chemistry that clean would be the mark of the first generation. In one of the more distant galaxies we've studied closely, there are features that some read as a possible signature of these pristine stars, a patch with the right kind of radiation and a striking lack of heavier elements. But every such hint sits at the edge of what we can measure, faint and ambiguous, open to more than one reading. A signal that looks like pristine stars might also be produced other ways, and the data at these distances rarely settles the question. So the honest status is that we have suggestive candidates and no confirmation. The difficulty is fundamental, not just a matter of trying harder. The first stars are faint, brief, buried in the most distant and most stretched light we can gather, and their defining feature is an absence, the lack of heavy elements, which is harder to prove than a presence. Proving something is missing, to the level of certainty the field demands, is far harder than detecting something that's there. You have to show not just that you don't see heavy elements, but that you would have seen them if they were present. That bar is high, and nothing yet has cleared it convincingly. And there's a real chance that even this telescope isn't quite enough to settle it. Webb has pushed the search closer than anything before it, catching light from galaxies in the right era and turning up these ambiguous hints. But confirming an individual population of the first stars cleanly may need either a rare accident of magnification like the one that solved the red point, or instruments beyond what we currently have. We've narrowed the hunt to the right time and the right kind of signature. We have not yet closed a hand around a single confirmed first star. Notice how much rests on objects we haven't confirmed exist. The first stars are what forged the initial heavy elements that made cooling efficient, that made dust possible, that enriched the gas the dust required. They provided some of the ultraviolet that helped clear the fog. Their deaths may have left behind the black hole seeds. Nearly every early puzzle we've followed traces back to this generation, and yet the generation itself remains at the edge of detection, inferred from its consequences rather than seen. We're confident they existed because everything after them requires them, not because we've looked at one. So we've reached the true frontier of what light can show us, and it's closer than the beginning. The first stars mark roughly the earliest thing a telescope like this could ever hope to see, since they are the first things that produced light at all. Before them there was matter and gravity and the slow gathering of structure, but nothing yet burning, nothing yet shining. Which means that just beyond the first stars lies a stretch of cosmic history that produced no starlight whatsoever, a region no telescope built to catch starlight can ever reach. What was the universe doing in the time before the first star switched on? Let's mark the boundary precisely, since it's a real line in cosmic history and not a vague one. After the ancient light was released, when the first neutral atoms formed, the universe was filled with glowing gas that then cooled and dimmed. Once that glow faded, there was no new source of light. No stars yet, no galaxies, no black holes feeding. Just neutral hydrogen and helium, spread thin, sitting in the dark, slowly being drawn by gravity into the denser regions of that seed pattern. The universe had matter and structure forming, but nothing was shining. We call this stretch the Dark Ages, and the name is literal. The darkness wasn't empty, and that's the part that matters. Underneath, the most important process in the whole story was quietly running. The dark matter was gathering into denser and denser knots, and the neutral gas was sinking into those knots, piling up, growing colder and denser at the centers. Everything that would later ignite was being assembled in that dark stretch. The gas that would become the first stars was collecting, compressing, approaching the conditions that would finally let it collapse and catch fire. The Dark Ages are where the first stars were made, in the dark, before they burned. So this era holds the answer to things we've been circling. When exactly the first structures crossed the threshold into collapse, how the gas actually gathered before any star existed to disturb it. Whether it assembled smoothly or in clumps, which is precisely the question that separates the dark matter models. The Dark Ages are the cleanest possible test of how structure forms, since there's no starlight, no feedback, no messy astrophysics of stars and explosions to complicate the picture. Just gravity working on gas and dark matter, in the dark. It would be the ideal thing to observe, if only it produced any light to observe. And that's the wall. A telescope like Webb catches light made by stars and hot gas and feeding black holes. In the Dark Ages, none of those existed, so there is nothing for such a telescope to catch. No matter how sensitive we make it, no matter how long we stare, there is no starlight from that era to gather, since the stars hadn't formed yet. This isn't a limit of Webb's size or its detectors or its position. It's a limit set by the universe itself, which produced no starlight in that stretch to be seen. The boundary isn't in the instrument. It's in what there was to detect. But the Dark Ages are not completely silent, and there's one thread of light they do produce. The neutral hydrogen filling that era emits a very faint, very specific signal on its own. A hydrogen atom has a tiny amount of internal energy tied to the arrangement of its electron and proton, and occasionally it releases a sliver of that energy as a single low-energy photon at one precise wavelength, 21 centimeters. Any cloud of neutral hydrogen, even cold and dark with no stars in it at all, quietly gives off this faint 21-centimeter glow. It's the one light the Dark Ages emit, produced by the neutral gas itself rather than by any star. That signal is our only possible window into that era, and reaching it is brutally hard. The 21-centimeter light from the Dark Ages has been stretched by the expansion of the universe, just like every other ancient signal, drawn out from its original short wavelength into long radio waves, meters across by the time it reaches us. Catching it means detecting an extraordinarily faint radio whisper from the whole early sky. And that whisper is buried under radio noise from our own galaxy and our own technology, sources vastly brighter than the signal we're trying to hear. Pulling the Dark Ages signal out of that noise is at the very edge of what we can attempt, and it hasn't been cleanly done yet. There are efforts underway, and they reveal how far we have to go. Radio arrays on the ground are trying to catch the 21-centimeter signal from the end of the Dark Ages, when the first stars were beginning to switch on and alter the surrounding hydrogen. Those are the more accessible signals from the very edge of the era, where the first light was just starting to touch the gas. The deeper dark ages, before any star at all, produce an even fainter signal, and reaching that may require something drastic, like a radio telescope on the far side of the moon, shielded from every trace of earthly noise. The cleanest chapter to interpret is the hardest one to hear. So we've arrived at a genuine edge, and it has a particular character. It's not that we've seen to the beginning and found the beginning. It's that there's a stretch of history right before the first stars that produced almost no light of any kind, and the little it did produce is a signal we can barely detect and have not yet cleanly captured. Beyond the first stars, the light thins to a single faint radio whisper, and then, before that, to the release of the ancient glow, and between those two lies the dark we can't yet properly see into. We can reason about it, model it, predict what it should contain. We just can't look at it, not really, not yet. And notice that this edge is where the whole crisis would actually be settled. Every model of dark matter makes a clean, specific prediction for how the gas gathered during the Dark Ages, without any starlight to muddy it. The elongated shapes, the fast assembly, the too early order, all of them trace back to how structure formed in exactly this unseen stretch. If we could read the Dark Ages directly, we could test the foundations without any of the astrophysical complications that make the visible galaxies so ambiguous. The answer to the crisis is written in the one era we can't yet observe. So the question that started this whole night, whether the early universe really broke its own rules or only broke our assumptions, waits on measurements we haven't yet managed to make. The telescope that opened the crisis cannot close it, since the deciding evidence lies in a stretch its light can't reach. Which turns us, finally, toward what comes after Webb. The instruments being built and flown right now, aimed squarely at the pieces of this that Webb alone can't resolve. What are we building next to answer the questions this telescope could only raise? Let's be clear about what kind of instrument actually settles a crisis like this. Webb is built to look deep, to gather the faint light of a few individual objects at the very edge, in extraordinary detail. That depth is what let it find these early galaxies and read their spectra. But depth on a few objects is exactly the wrong tool for a problem that turns on numbers. When the question is how many bright galaxies exist too early, or how the shapes are distributed across a whole population, staring deeply at a handful of them can't answer it. You need to see a great many across a wide stretch of sky all at once. That's a different kind of telescope, and one is nearly ready to fly. An instrument built not for depth on a few targets, but for width across enormous areas of sky. Its field of view takes in around 100 times more sky in a single frame than the older wide-field telescopes managed, while holding comparable sharpness. So instead of one deep pinpoint, it captures vast fields containing enormous numbers of galaxies in each exposure, building catalogs not of dozens but of billions. This is the Nancy Grace Roman Telescope, finished and scheduled to launch within months, headed for the same distant vantage as Webb. Numbers on that scale change what the anomalies even are. A handful of impossibly early galaxies can always be a statistical fluke, a few rare peaks we happen to catch. With billions of galaxies mapped across huge volumes, the counts stop being anecdotes and become distributions, precise enough to say whether the early bright galaxies are a genuine excess or a small number illusion. The same holds for the shapes. A wide survey measures the elongation of vast numbers of early galaxies, turning the contested hint about prolate forms into a statistical statement solid enough to test the dark matter models against directly. And that width feeds a second, deeper measurement, one aimed at the framework itself. Recall that the way light bends around mass reveals gravity beyond what visible matter can account for, which is how we sense dark matter in the first place. Across a wide enough field, this bending shows up as a subtle, coherent distortion in the shapes of background galaxies, warped slightly by the mass lying between them and us. Measure that faint distortion over billions of galaxies, and you can map where the dark matter actually sits and how its distribution has changed over cosmic time. A wide survey doesn't just count galaxies. It weighs the invisible framework behind them. There's a companion effort already underway from a separate instrument, working the same problem from a different angle. A survey mapping the positions of enormous numbers of galaxies in 3 dimensions, charting how they cluster across a large fraction of the sky. The pattern of that clustering, how galaxies gather and space themselves across cosmic time, is itself sensitive to the nature of the dark matter and to the expansion driving everything apart. Between the 2 efforts, one weighing the invisible mass through the bending of light, the other tracing it through the arrangement of galaxies, the framework gets tested from 2 independent directions at once. We saw that the Dark Ages, before any star, offer the purest test of how structure formed, uncontaminated by starlight. No wide-field telescope catching starlight can see into that stretch, since there was no starlight in it. Reaching it means a completely different kind of instrument, one built to catch that faint 21-centimeter radio whisper from the neutral gas, stretched now into long radio waves. Arrays of radio antennas, spread across quiet ground and shielded from human interference, are being built and expanded specifically to listen for it. Those radio efforts are the hardest and the furthest from success, and it helps to be honest about that. The signal they're chasing is buried under noise thousands of times stronger, from our own galaxy and our own machines. Pulling it out cleanly, especially for the deepest part of the Dark Ages, may ultimately require putting a radio telescope somewhere truly shielded, like the far side of the moon, where the moon's own body blocks every trace of earthly interference. That's a longer horizon than the wide-field surveys, measured in more than years. The cleanest answer to the whole crisis is also the one furthest out of reach. So the tools that will actually resolve this arrive on a staggered schedule, and it's honest to lay that out plainly. The wide surveys are nearly here, and within a few years they should tell us whether the early excess and the strange shapes are real or artifacts of small numbers. The mapping of the invisible framework will sharpen alongside them over this decade. And the direct reading of the Dark Ages, the deepest test of all, waits on instruments and locations we haven't finished building, on a horizon that may stretch well past this decade. The crisis opened suddenly. It will close slowly, in stages, each instrument answering the part of it that it alone can reach. I keep returning to how ordinary that pace actually is, against how the discovery felt. The finding arrived like a shock, a telescope switching on and immediately seeming to break the timeline. The resolution won't arrive that way. It will come as a slow tightening, survey by survey, measurement by measurement, some cracks closing quietly as better data explains them, others perhaps widening into something genuinely new, over a span of years that will outlast the excitement that opened them. That's the actual rhythm of settling a question this large. Not a moment. A decade of careful looking. And while all of that unfolds far from here, the thing that started it hasn't stopped for a moment. The oldest light is still arriving, still falling on the gold, still being sorted and measured 1,000,000 miles out beyond the moon. It's falling on other things too, on the ground, on the roofs, on the dark fields where the radio antennas wait. It's falling, in its faintest and most ancient form, on the room where you're lying right now. What does it mean that the same light we built all these instruments to chase is passing through you as you listen? Let's end with the light you're making right now, since you are making some. Your body is warm, and everything warm radiates. The same physics that told us why Webb had to be frozen and shaded tells us this. Anything with a temperature above the cold of deep space gives off light, and the temperature sets the color. Your body, at its ordinary warmth, glows steadily in the infrared, pouring out light at wavelengths a little longer than the reddest your eyes can see. You are, at this moment, a source of exactly the kind of light Webb was built to gather. This isn't a figure of speech, and the numbers make that plain. The light you emit peaks at a wavelength around 10 times longer than visible light, squarely in the infrared band. It's why a thermal camera can find you in a completely dark room, reading the glow of your own body heat. The gold on Webb's mirror was chosen to reflect these long infrared wavelengths well, the same range your skin is radiating into the dark around you as you lie there. The telescope and your body are working in the same band of light, one catching it from the beginning of time, the other producing it under a blanket. And the ancient light is here too, in the room, not as an image but as a physical presence. The oldest radiation in the universe, the glow released when the first atoms formed, never stopped traveling, and it fills all of space evenly, including this space. It's been stretched by all the expansion since into faint microwaves, cold and low in energy, but it's genuinely present in every cubic meter around you. There are hundreds of those ancient photons passing through each cubic centimeter of the room, right now, left over from a time before any star. The beginning we spent all night reaching toward is not only far away, a trace of it is in the air above your bed. So the whole scale of this collapses to something close. We followed light from a galaxy that shone before the sun existed and worked out how much its color had stretched and used that to weigh the impossible speed of the early universe. The physics that let us read that light is the same physics running in your own chest. The radiation of warm things, the stretching of waves, the way a temperature sets a color. These aren't separate laws for the cosmos and for the body. They're one set of rules, operating on a galaxy at the edge of time and on the person lying in the dark listening, with no change but the scale. Almost everything we followed was a crack, a place where the early universe outran our understanding. The masses too large, the order too soon, the fog cleared too fast, the shapes too strange. But the physics of light itself never wobbled once through any of it. The rules that describe how a warm thing glows, how a wave stretches, how an atom emits at a fixed color, held perfectly, from the gold mirror 1,000,000 miles out to the warmth leaving your skin. The story was full of uncertainty. The light it was written in was not. That's the strange comfort under all of tonight's unease. We don't know what the dark matter is, or how the first black holes formed, or why the early universe assembled so fast, and we may not know for a decade or more. Those questions are real, and they're open, and the instruments to answer them are still being built or still climbing toward the sky. But the same light, carrying all those unanswered questions, is also the light your own body is quietly giving off into the room. The mystery and the familiar turn out to be made of the same thing. So there's nothing you need to resolve before you sleep. The oldest light is still falling on the gold, 1,000,000 miles past the moon, and it will keep falling whether or not anyone is awake to sort it. The faint ancient glow is still drifting through the room, unbothered, as it has for nearly the whole age of the universe. And your own warmth is still radiating gently into the dark, the same kind of light, obeying the same rules, asking nothing of you at all. You can let all of it continue without you for a while. The physics does not need you to watch it to keep working. Thank you for staying with me through all of it, out to the edge of what we can see, and back again to the warmth of your own body in the dark. There's a great deal we still don't understand about how the universe began, and there will be more nights to follow it further as the new instruments start to look. For now, though, you've come far enough. Let the old light fall where it falls. Rest easy and sleep well.